Hi, ladies and gents. We've been talking about bonding all last week and this week in our course, and there are a whole variety of different bonds. So I wanted to spend just a couple minutes putting them all next to each other so we could kind of compare and contrast them. And I wanted to look at relative strength. So we've talked about covalent bonds, ionic bonds, we've talked a little bit about metallic, and in this video, primarily we're going to talk about hydrogen. But if you look from strongest to weakest, the strongest kind of bonds there are those covalently bonded network solids that hold together things like mountains, quartz, and diamonds. And it has a lot to do with the structure of those molecules. The next weakest are those ionic bonds. Those hold together those minerals and salts. How do we know they're so strong? Salts have really, really high melting temperatures, which is a big hint to how strong something is bonded. Then we have those metallic bonds, that sharing of that sea of outer electrons. And even within metals bonded to other metals, you have some things that are relatively weak, like aluminum foil that you can tear with your hands. And some metals are very strongly attached to each other, like titanium and tungsten, that can be used in creating superjets and creating replacement joints. Then there are the covalent bonds that are not network solids, but these are simple shared pairs of single, double, or triple bonds. These make the squishy bits that make you, me, plants, animals, food, and fuel. But what about wimpy little bonds, temporary bonds, things like Post-it notes that sometimes bond and some don't? Those are hydrogen bonding. So we're going to take a fast and furious look at these here. Now, if we look at covalently bonded substances that involve sharing electrons, sometimes those electrons are not shared equally. Some of you can relate to this picture. You might share a bed with someone or a critter that hogs the bed once in a while. Same thing happens with electrons. Very often, if hydrogen is involved, and that's why it's called hydrogen bonding, hydrogen is a wimpy little atom. Hydrogen has one proton in its nucleus, so it does not have a lot of electrical power that allows it to greatly attract electrons. Oxygen is sitting here with 8 protons in its nuclei. Each hydrogen only has 1 proton. So the electron cloud around a water molecule is not going to be evenly distributed. That electron cloud is going to be greatly skewed, so it is more near the oxygen. If we have hydrogen and chlorine, hydrogen's got that little tiny wimpy 1 proton. Chlorine's a big beast here. It's got 17 protons in its nucleus. If you have hydrogen chloride bonded together, that electron cloud is going to be way skewed off to one side. All the electrons are going to be really much more attracted to the more electrically powerful chlorine than that wimpy little hydrogen. So the electron cloud is not going to be evenly distributed. What that produces is something called a polar molecule. Just like a magnet will have a north and a south pole, these magnets are going to have an electrical pole, one side being a little positive and one side being a little negative. If we have a water molecule, the electrons are going to be more towards the oxygen end, making that oxygen a little negative, and the hydrogens a little bit more positive. This makes the water molecule polar, meaning that it's electrically not neutral. It's not neutral all the way around. There's kind of a polar nose, a negative nose on it, and a positive nose on it. Kind of depends on which direction you look at it from, whether you see that slightly positive or negative end of the molecule. So when you are dealing with hydrogen bonding, what's going on is when that slightly polar negative end and that slightly polar positive end attract. You know from electricity, from the years you've been in school, that like charges repel and opposite charges attract. So if we have 2 water molecules and the oxygen end tends to be a little negative, the hydrogens tend to be a little positive, those opposite ends of that water molecule are going to attract to each other because opposite charges attract. That little electrical attraction right there, that is going to cause a hydrogen bond. That hydrogen bond in water is what holds water molecules to other water molecules that makes liquid water. Now, when we boil water and make steam out of it, what we break, what we actually destroy when we add that extra heat is we destroy these wimpy little hydrogen bonds and let each little water molecule separate from the next. Is it pretty easy to go from liquid water into steam? Absolutely. Most of us do it every day or so when we boil something on the stove or boil something in our microwave. So it's not hard to do, and these are not terribly strong bonds. So let's get an official definition of a hydrogen bond. It's a weak electrical interaction between molecules due to a polar covalent bond. Polar meaning not the same all the way around. Now, this doesn't happen very often. It happens most often when you have bonds between hydrogen and fluorine, oxygen, chlorine, or sulfur. And these become less polar as you go down. Now, why hydrogen and these other things? Remember, hydrogen's a little electrically wimpy. It has one proton in its nucleus. And all of these have a lot of proteins, a lot of protons in their nucleus. So these are much stronger, and they are all going to have a greater electrical attraction to the electrons, and they are going to cause those molecules to be polar. So how does this affect life? Well, hydrogen bonding often causes weak attractions that can be created or destroyed by water. Here's a handful that you see in your normal everyday life. Your contact lenses sticking to your eye. I wear contacts. And when I put my contacts in my eye, what holds them there? You don't use glue. You don't use any sort of stickum that sticks them there. It's moisture. It's that tiny little layer of water, tiny little moisture layer that keeps the contact in the eye. And at the end of the day, when you take your contacts out, you just get in there and pop them back out again. But what holds them there all day long? It's these hydrogen bonds. It's this weak little polarity of the water molecules. Hair. Okay, curling your hair. Whether you use a curling iron or you use rollers on your hair, you spend time and energy curling your hair. Okay, some of you are saying, Mary, I've never curled my hair in my life. So just relax for a moment while we talk about curling hair. When you curl your hair, you are creating some hydrogen bonds. And whether you get caught out in the rain or you take a shower, those weak bonds are destroyed by water. You get them wet and those bonds go blip and they're gone. And it's happened to many of us, and it's like, oh, there goes my pretty hair. It's gone. These weak hydrogen bonds are what makes water droplets have this cool shape. You look at a water drop from the side, and it has this nifty little shape. It sticks above the surface of a tabletop or a piece of glass or whatever. What holds the water into this nifty little shape? That's those hydrogen bonds, the water molecules attracted to each other. What holds water droplets to a window pane? Hydrogen bonds. This is another one that I think is kind of nifty. I don't know about you, but when I put my jeans on fresh out of the wash, they have a tendency to be a little tight. Now, it has nothing to do with the fact that I might have put on a pound or two. Yes, I'm joking there. But why are they tight when you first put your jeans on and by the end of the day, they're loose? So what's going on there? Now, I know these are two totally different pairs of jeans. I get that. But what's going on? What happens is there are little bonds between the fabric that are linked, little linkages that are created in the wash. Between that washing and drying process, these little linkages are created. And all day long, as you wear your jeans, these linkages are broken and they become loose. And then you put them back in the wash and they get tight again, and then all day long you wear them, they get loose, and then you wash them and they get tight again. It's not your imagination, but those little weak bonds that are easily broken, those are hydrogen bonds. Now, it doesn't have to involve water. one of the classic and best examples, 3M came up with a product many, many years ago, the Post-it note. And there are other brands that have similar technology today. But this is a weak adhesive, such a cool weak adhesive that you can stick it on something and then unstick it and restick it and unstick it. That's actually kind of magic because they are employing that hydrogen bond. It is something that is easily stuck and unstuck. They are using that property to create a weak adhesive. Now, those of you who have ever painted your home, you want tape that you can put on around someplace before you tape and then unstick it again. Those are these wimpy little hydrogen bonds. And here's the one for those of you who are going to go into the health world, that is the biggie. The beautiful double helix structure of DNA. What gives it that structure? Hydrogen bonds. What actually pulls it into that lovely shape? There are hydrogen bonds that are deep within our DNA. And if there is a piece of radiation that comes in that happens to break one of those and causes a new linking or a new structured or a new coupling to occur, that can possibly cause a mutation. And we've talked about radiation in the past. That radiation can be damaging because of the fact that it can easily break one of those wimpy hydrogen bonds. A lot of them won't cause any damage at all, but if it happens to be on an important piece of DNA in an important spot, then it can cause cancer or some birth defects. So we've been talking about bonding. Big overview. Remember, all of the types involve one atom or molecule interacting with another. All of the types depend upon the elements and where they're located on the periodic table. The periodic table is the key of determining who's going to bond with what, and how. If you're talking about ionic and covalent bonds, why is that happening? It's happening to achieve that full outer energy level. That's the holy grail in chemistry. If you're talking about metallic and hydrogen bonds, that's all electrical interactions. And those electrical interactions, electricity, is what holds all matter and chemistry together. Why is the Fast and the Furious over here? To remind me to tell you that what we've been talking about is a fast and furious overview of all of these topics. And this is a basic or beginning chemistry course. Please take more chemistry. It's a fascinating field. That's why people get gobs of PhDs in it. And I hope you enjoy. All right, we will see you next time. Bye-bye.